Okay, now we go on with Taylor's theory, and in particular with Taylor polynomial. And so the theorem we want to prove is the theorem due to Taylor, so the name is exactly Taylor's theorem. That says there's a function f of class Cm x bar in AB, and the statement has been already given in last lecture, so I just repeat it here. Don't look for news here because there are no news. Pm of x is equal to sums for j going from 0 to m of aj x minus x bar to the power j. So we can expand this sum and write it in a plain way, a naught plus a1 x minus x bar plus up to the last term, which is am x minus x bar to the power m. Okay. Now the distance between the function f and the polynomial pm is Lieder law of x minus x bar to the m power if and only if aj is equal to f j's derivative computed at x bar divided by j factorial for every j equal to 0, 1, up to m. Of course, for a equal to 0, here you have the function divided by 1. 0 factorial is 1. And now, let us prove it. The proof we use, it is a very simple proof because we use it's somewhat unstable, this iPad. However, we use the fundamental lemma of Taylor's theory, that says, remember that if f minus pm is Lieder law of x minus x bar as x goes to x bar, this means that the jth derivative of f minus pm, which is exactly the difference between the jth derivative of m and the jth derivative of pm, computed at x bar, are all equal to 0, all this derivative for every jth from 0 up to m. Okay. So we want to prove that fj of x bar minus pm, so to say fj of x bar is equal to pmj of x bar equal pmj of x bar for every j from 0 up to m if and only if this condition is satisfied. Aj is equal to fj of x bar divided by j factorial for every j. And this is just a matter of computation. Just let me do it quite explicitly for j equal to 0. Just for clarity, we could immediately go for the computation of the j's derivative, but we compute a0 explicitly. So we have f 0x bar is equal to pm 0 of x bar. This means, by definition of the zeroth derivative, that f of x bar, the zeroth derivative is the function, is equal to pm of x bar. But pm of x bar is equal to sum for j going from 0 to m of aj x minus x bar to the power j evaluated at x equal to x bar, and this is equal to a0. So a0 must be f of x bar according to the theorem, because with j equal to 0 this is a0 f of x bar. Now we generalize the computation to any j from 0 to m. Okay. So we have that pmj's derivative computed at x bar is equal to the derivative of the sum we call it k here, otherwise there is some confusion here. So ak x minus x bar to the kth power to be differentiated j times. Okay, this means that since the derivative is linear, the second derivative is linear, so the j's derivative enters into the sum, and here we have x minus x bar to the power k to be differentiated j times. Now let us focus on this x minus x bar to the power k to be differentiated j times, and of course evaluated at x equal to x bar. Now we already made a comment on that, and so we have to distinguish 3 times. If we differentiate less then the degree of the monomial. Then after the first derivative, we obtain a factor k, and x minus x bar to the power k minus 1. We differentiate again, we obtain k minus 1. And then, after differentiating j time, we obtain j factors, so from k minus 1, and then k minus j plus 1, x minus x bar to the power k minus j, okay, to be evaluated at x bar if j is less than k. If j is equal to k, here we just have k factorial. When we differentiate power of the variable exactly how many times, how large is the power, then we end up with the factorial. And if we differentiate further, we are differentiating a number here, so we find 0 if j is larger than k. Okay, here you can evaluate at x bar. So when you evaluate at x bar, you find that if j is less than k, then here this power is positive, so when x is equal to x bar, you obtain 0. For the rest, it is easy, because if j is equal to k, you obtain k factorial here, and if j is larger than k, again here you obtain 0. So here we go back to Pmj of x bar. And we have that the only surviving term here, if j is equal to k. So we have aj j factorial. Okay, now we impose this condition here. So the condition fj of x bar is equal to pmj of x bar. Reads then aj equal to pmj of x bar divided by the factorial of j. And this is the end of the proof. It is an if and only if, because in the lemma there is the if and only if. Okay, and this is the proof of Taylor's formula and of Taylor's polynomial. Okay, and now we can also consider other functions, other examples than those I proposed in the last lectures. So they are always Maclaurin polynomials, which means Taylor with x bar equal to 0. So we had the sine, now we go to the cosine. So f of x f of x is equal to the cosine of x. So f of 0 is equal to 0. F prime of x is minus, sorry, f of 0 is equal to 1. Minus sine of x, so f prime of 0 is equal to 0. F second of x is equal to minus cosine of x, so f second of 0 is equal to minus 1. F third of x is equal to sine of x, so f third of 0 equals 0, and f fourth of x is equal to cosine of x. So you see that after 4 iterations of the derivative, they repeat, and also the coefficient repeat. So like for sine, we have that f, sorry, let me do, if you take the cosine of x and you differentiate j plus 4 times, this is equal to differentiating just j times. So the coefficients without the factorial at denominator are 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on and so on. Then Pm of x, and that it is made, so nota bene, it is made only by even terms, only even terms are present, and Pm of x sum for j from 0 to m of x to j, because here there are only the even terms, divided by 2j factorial, and here there is a minus sign, okay, to take care of, because here when j is equal to 0, so we have f0, 1 is positive. When j is equal to 1, we are at f second, and this is negative. So here we have to write minus 1 to the jth power. And cosine of x is equal to this Pm of x. In the notation here, I lose track of the function of the cosine and of the point 0, but just for using a not too heavy notation, plus little o, be careful now, of x. That is that here the polynomial Pm, sorry, this is not Pm, I was wrong, this is P2m. P2m is of degree 2m, so this is little o of x to the 2m for x going to 0. And this is the first example. Another example of today is, for instance, the tangent. Now we had sine, cosine, so the tangent. F of x is equal to the tangent of x. So f of 0 is equal to 0. Here it is comfortable to use this version of the derivative of the tangent. The derivative is always the same. You can write it in different way according to different functional and trigonometric identities. So f prime of x is 1 plus tangent squared of x. So f prime of 0 is equal to 1. F second of x is what? Here you have to differentiate here, and you have two times tangent x, and then you have to differentiate tangent x, so 1 plus tangent square of x, so you have f second of 0 is equal to 0. F third of x is the derivative of this guy here, which is 2 tangent of x, so 2, 1 plus tangent square of x, plus 2 tangent cube of x, so 3. Tangent square of x, and here 1 plus tangent square of x. So at the end you have this polynomial, which is okay, 3 tangent 4 of x, then plus 2 plus 3, 5 tangent square of x, plus 2, and so f third of x is equal to 2. Now, it is not really meaningful to try to give a closed formula for the coefficients, but what you find at the end is that the tangent of x is here, f of 0 is equal to 0, so we start from 1, so we have here x divided by 1 factorial, and then plus 2 over 3, so here you have x3 divided by 3 plus little o of x3 as x goes to 0. Notice that here, so a remark, since sine of x is equal to x minus x cubed over 3 plus little o of x cubed, tangent, over 6, not over 6, sine of x. And tangent of x is x plus x cubed over 3 plus little o of x cubed as x goes to 0, then at least in a neighborhood of 0 in which little o of x3 is negligible, then one has that sine is less than x, less than the tangent. This is always true, okay? Always true, at least in minus pi over 2, pi over 2. And this was used to prove that sine of x divided by x tends to 1 as x tends to 0. And indeed, to be really rigorous, I should not use pictures and intuitive geometric construction, even though they seem to be very clear. And in a rigorous course of analysis, sine and cosine are defined starting by Taylor polynomials and Taylor series. And then you immediately see that. This is just so for people who want to do things very rigorously. The point is that in this way you don't see so much you have this definition of sine and cosine with the series, but then it is not really clear what happens there. Okay, and the last two examples I want to do here are the following. The third is of course, the hyperbolic sign. You know, I like hyperbolic functions. So f of 0 is equal to 0. F prime is the hyperbolic cosine of x. F prime of 0 is equal to 1. F second of x is hyperbolic sine of x. So f second of 0 is equal to 0. And so you see that here you have a periodicity 2. After 2 repetition, the function is the same, so hyperbolic cosine of x, j plus 2, as a function is hyperbolic sine of x, j. And the coefficients are 0, 1, 0, 1, 0, 1. So what you have is that Pm of x for the hyperbolic sine is the sum for j from 0 to m. Only even terms here survive. So again, you have x to the power 2j plus 1 divided by j factorial. So it is the same as for the case of sine, but with positive terms, so with no factor minus 1 to the power j. And very same thing happens for f of x equal to the hyperbolic cosine of x, because it is the same. So f prime is the hyperbolic sine of x, f second the hyperbolic cosine of x, and f of 0 is equal to 1, f prime of 0 is equal to 0, f second of 0 is equal to 1. So, sorry, and here what I did not write is that f of x is equal to Pm of x plus Lido law of 2m plus 1, x to the power 2m plus 1. And here this time we have that Pm of x is made only by even powers. So sum from j from 0 to m, x to the power 2j divided by j factorial. And in this case it is the same as for hyperbolic cosine of x. But we know oscillating sine, and again here we have this correction to be done. Okay, and so this is all for this example, and then in the next lecture I will give other examples.